Hello and welcome back to Precalculus, the section for today on 6.3 on polar coordinates. And we are setting up the scenery for Calculus 2, Calculus 3, where polar coordinates are used to describe certain functions that are not really friendly in x and y. Let's call it a realm. It's the mathematical space, but let's call it a realm. So xy realm. So you are used to what we call Euclidean space, Cartesian coordinates, x and y, where by counting on, let's say, x, and then counting on y, you reach the point, and you can, in general, we go down x-axis and then we follow go up or down to reach the point, and then the point is oriented as written as 4 comma 2, where 4 is x and 2 is y. Now you could get to the same point if you do the y first and then go with x, but in general we don't do that. You can reach the same point, right? But we in general, as I said, we don't do that. And you have learned a lot of these functions like x squared function and sine function and a whole bunch of different functions that you can draw in this coordinate system. And this coordinate system, like each line, each function, is a collection of infinitely many of these points, all stuck next to each other, right? Going like that. Now, what we want to discover in this section is a new way to reach to the point. So we don't want to go along x-axis and then go 90 degrees up or down. Now we want to use a different approach. What I want to do now to reach, let's say, the same point 4, 2, which is right here, instead of going to 4, I'm going to go a little bit longer past 4, a little bit further away. I don't know how much yet, but I'm going to go some amount further than 4. So see, 4 is right here, and I'm going to go all the way up to there somewhere. And then I'm going to pick this up and swing that with the angle this way, angle theta, and I'm going to hit and stay at point 4, 2. So in this case, in the first case, I was counting all the way to 4, counted 2 units up, and we were good to go. But on the right-hand side, we actually went past 4, and then we swing into the side on to the left, counterclockwise, and we get to the same location. So what we used in this case, in the second case, is the length r, which is the radius that we draw out, and then we swing angle theta, in this case counterclockwise, and we get to this point 4, 2. Now, I don't know yet, we're going to discover formulas and ways to tell, but I don't know yet how far we went out with r, and I don't know how far we swing with theta, but at least we see that it's possible to get there using this new weird way, right? Because you're used to moving in straight lines and then just go up or down. Now you still go in a straight line on x-axis to get this r, but then you swing across, right? And you swing across, which gives you the this kind of arc movement, the arc length, right? And you end up at the same place. So something like this would be known as polar coordinates. And we use them, right, to reach the point in a different way. Now, it looks like an overkill because we're talking about 4-2 point, but we'll see that actually this is very useful. And as much as it doesn't look like it right now, we will very quickly realize that it's used to simplify a lot of really nasty stuff that you can't do very well with X and Y graphs. But let's build up to that point. So let's just graph some points first, and then we'll deal with why would we need polar coordinates and all that good stuff. So let's say that the point is given to you as 3 and pi over 4. Right? How do we graph this? Well, we see this is still xy graph, so it's just the way to get to places, right? It's polar coordinates. So we're going to stretch this radius of 3 all the way to number 3. And then we are going to swing that at 45 degrees. So let me first make a construction line for 45 degrees. That's your pi over 4. And now, when I swing this over, it creates this point, and that point there is 3 pi over 4. You have your radius r stretched, which means that this one is also going to be the same r. And then you have the angle in between them, which is this angle here, angle theta, in our case, pi over 4. So what's the star of the show? The star of the show is this point, because that's what we were supposed to graph. But in order to graph that point, right, we had to first figure out the radius and the angle. Now, let's try another one. How about 2 and negative pi over 6? 2 and negative pi over 6. Well, negative angles. Positive angles, right? So, we draw 2, radius of 2. That's a radius r. And then negative pi over 6 is negative 30 degrees. Construction line should go right there. That's too steep. I mean, needs to be steep. So we swing this right there, and there's your point. So we went negative pi over 6. Pi over 6 is 30 degrees, and when it's negative, we go down. When the angles of the additive angles are positive, we would go counterclockwise. In this case, we will go up. But since we have a negative pi over 6, it swings downwards, and we have our point. Now, can you have a negative radius? The answer is yes. Negative 3 and pi over 3, doesn't matter. Now what you need to know is that your graph is supposed to start on the left side because r is negative in this case. So 1, 2, 3. This over here is now your r. So now pi over 3, again, counterclockwise is for positive angles. So pi over 3, that's going to give us 60 degree in this quadrant. There we go. And now we swing there, and that's our point. So you can have negative. Just like you can have negative angles, just go the other way. Right? Up is, in this case, right? Up is positive and down is negative. Now, for these polar graphs, it's important to understand that if you are to go another full circle around, you are going to land in the same spot. So you have to be aware of that. I mean, we did that before when we talked about reference angles, right? And we said you take full revolutions away, and then once all the full revolutions are away, then you focus on getting the leftover angle into the first quadrant, which would be reference angle. So now, if you go a couple of times around the circle and you end up at the same dot, well, you still have the same polar coordinates for it. And it doesn't matter that you went around 5 times. Now, what is the connection of this polar coordinates with what you studied before? Is there conversion? Is there anything that kind of keeps these two separate but yet connected? And it turns out, yes. If you have a situation, right, just in general, where you have your radius r stretched to some point. Now that point has coordinates x, y, and we can get that y and get that x over here. What we see is a right triangle, and we know Pythagorean identity for it. Pythagorean theorem. And this is our angle theta. Because we know Pythagorean theorem, we can write that x squared plus y squared is equal to r squared in this case. And now what do we do for r squared? Well, you solve that for r by square rooting both sides and ignoring the negative because lengths are never negative. And look, we have a formula, a conversion. Because we have the formula that it's a conversion formula that converts x and y, in this case, into r. I need one more formula, and that's going to be tangent theta formula, which in our case is y over x, opposite over adjacent. And from that formula, I can solve for theta by using the tangent inverse. So what we have with these two formulas is ability to convert from Cartesian system into polar. So Cartesian system into polar. We'll have two equations. equation r squared plus y squared, and theta to come up with those two values that you need to put in the parentheses, right? Now, we can also write sines and cosines for this. So sine theta is y over r. Well, solve it for y, because you have theta and r. So if you have those as input, right, you leave that as input. And then r, which is single, has no theta with it, is just going to be the output. So y equals r sine theta. And similarly, if you use cosine, which is x over r, you will find that x is equal to r cosine theta. And finally, let's put on the side, we have polar to Cartesian, and you have your x equals r cosine theta and y equals r sine theta. Go away. So there they are. Two conversions. So now we can turn polar into Cartesian and Cartesian into polar. Now, why would we want this? Well, let's check how nice is our point 4,2 in polar coordinates. So how nice is 4,2? Convert 4,2 into polar coordinates. All right, we have our formulas. We take r equals square root of 16 plus 4, it's the square root of 20, which is 2 root 5, because 20 is, yeah, okay, root 20, that's 4 times 5, square root of 4 is 2, so we're all good. And now we need our inverse tangent. Now for this you will probably be reaching for the calculator, which is okay. Tangent inverse of 1/2. Now you need to make sure that you are in degrees or you're in radians. So you can leave the angle. In this case, we generally like degrees because this is applied in a lot of mechanical and other engineerings. So let's see. Inverse tangent of 1/2 is 26.57 degrees. So we have our 2 root 5 and then 26.57 degrees. Is anyone going to comment on how weird this answer looks like? I guess not. Okay, fine. I'm still going to tell you that you are not going to find too many cases where both of these coordinate systems perform well on that particular function. What we have, for instance, in this, well, actually, let's do it this way. I like to say what's beautiful in polar, it's bad looking in Cartesian system. And what's beautiful in Cartesian system is going to look bad in a polar system. Because these two systems don't compete, really. They are designed for different types of application. Polar coordinates want to deal with circles and ellipses and round things, where the Cartesian coordinates want to deal with straight lines and squares and edges and corners and things like that. So these two do not compete. They complement each other. Right? One is doing one thing well, the other one is not doing well in the same. And we'll see that one more time prior to ending the lesson. So let's jump into homework and take a look at some of the problems they have. They say I want the conversion problems. I mean, that's fine. We can just pick any one of these and keep converting. So let's take a look at problem number 30, where you have -2, 7 pi over 6. Now, this problem is asking you to select representations that do not change the location of the given point. And they give you a couple of options. But you know what? I want to convert this. And the way we do this is, see, you have r given and you have theta given. So you will use the formulas that calculate x when r and theta are given. So x is equal to r cosine theta, which is -2 times cosine of 7 pi over 6. And now the question is, how much is cosine of 7 pi over 6? If you draw, right, 7 pi over 6, that's 1 pi over 6 more than pi, which is 6 pi over 6. So if you take a look at this, right, it's a long way to get there, but it's still in the first rotation, which is good. It's not in our first quadrant though, but that's what we have reference angles for. All students take calculus. This one is positive, and then yeah, that's A is all positive, sine positive, tangent positive, cosine positive. So we have a negative there, so that's just going to give us 2 cosine of pi over 6, which is 2 times root 3 over 2, which is just root 3. So we have the first coordinate, it is root 3. Now we rinse and repeat. -2 sine of this one, so I have sine of, yeah, so there are no changes in sine, 7 pi over 6. So now, since this is a point, well, actually we can compute this, hold on. That's a -2, And then sine of 7 pi over 6 is the same. That will be a negative, so that's going to kill this negative. 7 pi over 6 is pi over 6. It's a 1/2. So times 1/2 equals to 1. Questions, concerns? No? Okay. Present these points. Root 3, 1. I mean coordinates as a point. Root 3, 1. And we have converted the polar into this Cartesian coordinates. Just want to make sure that I did not miss anything. No? We're all good? All right, I will give you one to convert. Okay, let's see. Convert. All right, try this one. Problem 19. Convert negative 2 to negative pi over 2. So convert that into xy. Go. You have 10 seconds. Use the same steps, guys. Right? So, x is negative 2 cosine negative pi over 2, and y is negative 2 sine of negative pi over 2. So, cosine is an even function, so this minus just goes away. Cosine of pi over 2 is 0, so the whole thing is 0. And in the in the second equation, we have the odd function, so the minus goes outside and makes that positive 2. And then sine of pi over 2 is 1. So this is 2. And the point is x comma y. All right. Trying to see if there are any other cool exercises. Let's talk a little bit about the basic graphs, and then that will be it for this. The graphing and all the details about everything else and more complicated graphs is going to be in your, as I said, in your calculus 2. But these are the two graphs that you should know when you learn basic polar coordinates. And those two graphs are a straight line graph that is not shifted up or down, it's a straight line graph, or the circle. So when you have an equation, in this case f of theta equals to r, the only thing that you get is the circle with the radius r. And when you compare that to your Cartesian coordinates, not so happy, right? Because well, I'm trying not to go in deep into Calc 2 and stuff that you guys are going to, so I have to be very careful. I can talk about this for like 3 hours straight. We have, see, theta is not part of this equation, which means this radius is going to trace, right, your starting point, is going to trace it all the way around because r is taking on all of the angles. Angles are not mentioned in the formula at all, so it traces the circle. But on the other side, if the function is equal to theta, that is just going to give you an angle through the origin. So that's a straight line. So circle and linear line. And these are the two basic graphs. It is really interesting to see, right, now you compare the two worlds, the polar world and Cartesian world. So what do you have here? R equals 6 to come up with a circle. In the Cartesian world, x squared plus y squared equals to 36. So which equation do you want to work with? Do you want to work with this? Or do you want to work with this? So in this case, choice for polar coordinates is warranted and better, right? And again, this is not a function. That's another thing. Where r equals to 6 is. But it's in a different coordinate system. So both of these would graph the same circle, but they don't even graph it in the same way. So that's it. The two basic equations, linear line and the circle. We talked about that, and well, that will be it. That's it, guys. Any questions, concerns? All right. See you next class. Bye.